Let us now conclude our study of energy in inductors. In particular, this is going to allow us to make connections to energy stored in the magnetic field, and putting that together with what other considerations we have made with regard to energy and the various Maxwell equations describing the magnetic field, we will begin to be able to piece together a very coherent field theory built around this concept of energy. Now, just to review some of the salient facts that relate to energy and inductors, you will recall that we were considering a simple LR circuit where we have a certain inductor with inductance L and resistance, and somehow we had managed to start off this circuit at time t equals 0 with some initial value of the current I0, and then as time goes on, because the inductor wants to maintain that current, if you wait a little while, the current doesn't immediately vanish, it decays over some time period. And as it's decaying, it is driving current through this resistor, dissipating power and heating up the resistor. So clearly there is some energy storage properties associated with this inductor. Now, in terms of the underlying physics, the key fact about the inductor we know is that it contains some magnetic field. So it is very reasonable to suspect that there is energy somehow stored in this magnetic field that is passing through the center of this inductor. As we begin to piece these things together mathematically, we begin to see some clues that perhaps, in fact, that actually is the case. The energy stored in the inductor we were able to determine, if we believe in conservation of energy, by computing the total energy that would be dissipated in this resistor as the inductor discharges. And what we determined was that that was 1/2 the inductance times the square of the current. Very reminiscent of the energy storage properties formulas, the types of things we had seen in the past in terms of capacitors. Further deepening this connection is the fact that the inductance itself has this form, where lowercase n is the number of turns per unit length in my solenoid, but you'll notice that the inductance itself is proportional to the volume. So it does begin to feel as though this energy storage is proportional to volume, that maybe indeed it is related to this volume which contains a magnetic field which we know is isolated to within the center of our solenoid. And finally, we have our standard formula that will maybe allow us to make connections to the magnetic field for the strength of the magnetic field then within the inductor, as just permeability of space times this winding, the number of turns per unit length, times again the current. So let's see then if we can actually relate this energy that we can get out of an inductor to the magnetic field. Now, to make that connection, I want you to recall something that we had seen previously, which was that the energy density stored in the electric field, we had a formula for that. It's defined, of course, as the total energy in the electric field divided by the volume of the system, capital V, put a little tail up there to make it a capital. And our formula for that was epsilon naught, the permittivity, over 2, times the square of the electric field strength. Now, it's very reasonable for us, I think, because we know that the electric and magnetic fields are sort of very closely related. There are these various transformations between the two. They are connected through special relativity. For us to think that just like for each point in space, the special property of electric field has a certain amount of energy associated with it, which goes like the square of that field times some prefactors, it's very reasonable to think that perhaps the energy density stored in the magnetic field, that there might be some such density, and if we define that as the total energy per unit volume, that we're expecting that this also, I'll put a question mark, this is our conjecture, goes something like the square of the magnetic field times, some kind of prefactor here in front. So let's see if we can make some sense out of all of that. So let's begin by looking, for instance, at the total energy associated with the magnetic field. Our guess right now, and we will be able to formalize this later on, but our guess is that the energy stored in the magnetic field for this particular system is the energy that we will finally get out in the resistor as this inductor begins to dissipate the energy that it has, as we heat up the resistor and reduce the magnetic field strength. So a good guess would be to say that the energy stored in the magnetic field is this energy that we can always get out of the inductor, this 1/2 Li squared. I'm basically saying, look, there's nothing in this circuit, really, that any place where it looks like we could really store any energy unless it is in the form of this field energy, some new kind of energy associated with the magnetic field. Now, in our next step, we can insert what we know about the inductance. The formula for inductance is given to us here, mu naught n squared times the volume. So it's mu naught times the winding density squared times the volume, which is the length of the inductor times its area. And this multiplies I squared. And now notice, this is very intriguing because this goes like n times I quantity squared. But n times I, we know, is proportional to the magnetic field. And we were hoping to find that magnetic energy went like the square of the magnetic field. So let's rewrite this in terms of magnetic field. That would give us, something like 1/2 mu naught. We have our volume term here that we will come back to, L times A. And then what's left is n squared times I squared. So that's Ni quantity squared. And I want to write this in a different form, but this would be n times I that goes inside of that quantity. Now, n times I, we definitely can relate to the magnetic field. N times I is nothing other than magnetic field divided by the permeability. So in here, which should be, by rights, n squared I squared, or Ni quantity squared, we can rewrite as the magnetic field B divided by the permeability mu. So when I do this now and multiply through, you'll notice I'll have a 1/2. I've got mu naught on top here, but I have two factors of mu naught on the bottom, right? Mu naught squared. So that leaves me one net factor of mu naught in the denominator. So let me make this 1/2 mu naught. The next thing that you'll notice is I have then this factor that very clearly is the volume that contains that magnetic field, L times A. So let's write that as factor of volume. And then I'm left with B squared over mu naught squared. We had handled the mu naughts, so it's just left with B squared. So in fact, we do find that just like the electric field, energies are associated with the square of the field strength. And we even see that the energy stored is proportional to the volume that's containing the magnetic field, so that if we were to compute the energy density, UB, as the total, lowercase u on this side, as the total energy, capital UB, divided by volume, what we end up with is some prefactor, which is just 1/2 mu naught times B squared. And so we have this wonderful, beautiful formula for the energy density of the magnetic field, which is exactly parallel to the one for the electric field. It's E squared. It even has a factor of 2 in the denominator, just the same in both formulas. And instead of having an epsilon naught, we have a mu naught. And the only little difference is that mu naught in this formula appears in the denominator as opposed to the numerator in the electric field case. But otherwise, those are almost exactly identical. So this is very nice. We have this very nice kind of a field theory beginning to develop because we see there's very parallel developments here between the electric and the magnetic fields. So once again, we have a very happy professor symbol.